Alright, hello, my name's Miguel. I am part of Ozbay's class for Fluid Mechanics of 2025. Right now I'll be doing part C of the final project that we're doing, and that is, which we'll be doing a flat plate along the flow inside a wind tunnel. That's what we're going to be simulating right now. So we're going to go fluid flow, and we'll just go fluid. I mean, you could also just use geometry and then fluent directly, I guess, but we're just gonna go like this, and then we're gonna start a new geometry. Okay, we're in here. Now we will start our geometry. So, based on our assignment, we have this will be basically a geometry right here. I'm just roughly sketch it out very crudely, and we'll fix it. Okay. What I'm going to do is just make sure they're all symmetric. Looks good. Now I want to center it, so I'm going to use the midpoint to center. Construction. First, let me dimension these first, though. This dimension here, according to assignment, is 1.212.192. Here we go. And then from here to here, 1.1176. Then from here to here is 1.5748. Inlet will be 0.6096. Outlet will be 0.889. Then our inlet will be 1.6256. There we go. Now again, I want this to be centered. There you go. Now it's all centered in all axes. And this is just a typical geometry that we used in part A for the wind tunnel. But now we will set up our plate. And you set up a regular rectangle here. Dimension it. And dimension it here. Later. Then I'll make both of these symmetric. Zero 0.5, and this will be 0.0005. Basically, like 1,000 times thinner around there, and that's it. Now we press D, go back to body mode, it'll create a surface, and we just name everything in here. Inlet, outlet, low, top, and then just box select. Make sure it's all selected. Yep, looks good. And then this will be plate. Okay, I'll just make sure it's selected. Looks good. Good. And that's it. We could close it and move on to mesh. Okay. Alright. Make sure we have our name selections. We do. Looks good. Now we're going to refine it. So we're going to select, well, no, not inlet. The nozzle. Number of divisions. Let's go 10 for now, just to see, because we're going to apply a bias here. Here, bias factor of, let's go 3. And then we will reverse it. Right there. Just make sure that the finer part of the divisions is pointing towards the test section that we're interested in. Then now we put our actual number, which will be 200. Yeah. Yeah. And this you could name it nozzle. Insert a new one. And this will be our diffuser. The original is 10, so we could just see our bias. Capacitor factor 3. Reverse this flow. And then 200. Diffuser. That is test section. And this, we're not doing any bias, we're just going to put it to 250. Yep, looks good. Next thing I'm going to do is we're going to put a method for triangles. Then after that, inflation. Right there. And start geometry selection, go name selections just to make this quicker. We'll select low and top. Just for now, the plate will be a different, we'll have different settings for the plate. We're going to do first layer thickness, 1E -5. And then maximum layers will be 60. And we'll do growth rate 1.1. The first layer height, this is what I've always used in FSAE. They always work pretty well, so we're going to use it. This one, name it. Add another inflation. This time will be on the plate. Now, same thing here, 1E -5. However, the amount of layers we're just going to put up to 40. And then growth rate will be 1.1. That's it. If we put it any higher than, like, let's say 50 or 40, it will give you an error saying, hey, you can't mesh it. And that's because of the very thin thickness of the edges. So keep it a little bit lower. Here, I'm going to name it. go. And now we generate the mesh. Wait, almost forgot element sizing 0.005. There you go. Now we generate the mesh. Okay, we're done meshing. It looks good, very fine. That's what we want, but not too fine where it just took forever to mesh. Oh, almost forgot something. We forgot the number of divisions for the plate. That was what we forgot. No big deal, just go back. And then in here, we're going to select the edges. Make sure your filter is off. Click apply. Number of divisions, and I'm going to go 250. Looks good. Good surface. And then insert new sizing. Let's just be the edges. Apply number of divisions, and I'm going to put 5. There you go, and we just rerun it. Okay, and there you go. That's more like it. The boundary layer is a lot more finer, and yeah, you can see how the edge is forming. It's not perfect. You could probably fix this up a little bit more, but I'd say it's good enough for what we need. So let's move on. Alright, we're here. We're going to use K Omega for our simulation. K Omega is pretty versatile. It works pretty well with low speed flows, so we're going to keep that. So yeah, it's pretty versatile. However, there is something you do need to keep in mind when using K Omega, which I will mention shortly. Fluids, we're just going to keep this as default. That's normal. That's good. Now, inlet, our calculated velocity will be 5.625. This velocity is calculated because we want a test section velocity of 15 meters a second, and to get that velocity in here, we will need, there will be a ratio between both the velocities will equal a ratio between the heights between here and here in a 2D case. In a 3D case, it would be a ratio between area, where essentially you would get V2 divided by V1 will equal H1 divided by H2, or A1 divided by A2 if you're using a 3D case. But since we're in 2D, we're just using the heights. And yes, this will be our velocity. Now keep in mind, well, yes, we have calculated the magnitude here. We are using a viscous physics to simulate. So the velocity in here will not be 15 everywhere. Rather, instead, it will be 15 close around here. Maybe in the middle, closer here, but not directly in the middle. This is to be expected. But Overall, the average velocity should be 15. But yes, but this is the calculated velocity magnitude that we get, so we're going to use that. Internal's good. Outlet 0 gauge pressure, that's default. You check if you want, but yeah, that's okay. And then low, like this is all good. We're keeping the low and top plates as walls because we're simulating inside a wind tunnel, so there we go. That's all good. Reference values. For this simulation, you don't really need reference values because we're going to get our coefficients of drag and skin friction by just calculating it with the forces we get from the simulation instead. That's because if we were to compute from inlet, this will be our reference area and velocity rather than inside the test section. Regardless, I'm going to put it as just compute from inlet, but it really doesn't really matter if you accidentally forgot this part. So yeah, that's good. Report definitions. We're just going to do a force report. Drag force on the plate. And then we're going to go drag. Print to console. Press OK. And just for fun, well, I'll just put drag coefficient. Whatever. Just to see. But you don't need it. This isn't really... This value is probably wrong. I'm just going to use it, maybe probably just play around with calculations, but what you do need is your drag. This is what you really need. So, there you go. Our monitors, we're going to be using 1e to the negative, let's say 5, or no, 4. Let's go a little faster here. 1e to negative 4. There you go. You could adjust this convergence criteria depending on what you want. I want to go a little faster, so I'm going to go 1e negative 4. But if you want a little bit more accurate results, go 1e negative 5 or 6. But yeah, this should suffice. Alright, we are all good here, and we could start running the simulation and initialize. Alright, simulation finished. So yeah. Now let's look at our drag. Compute. And we got 0.63 newtons. Seems alright. Looks good. Nothing out the ordinary. Now let's check our mesh. To check our mesh, one way to do it is like this. If you're using K omega, or I believe also K epsilon too, you will need to look at your wall Y plus, which is basically like a turbulence parameter right here. And essentially for anything like, you know, not like going, for anything that's not going like over like Mach 1 or something like that, I'm not sure about the value, but it's around like the speed of sound, somewhere around there. If it's under that, like, you know, low speed, if it's incompressible, you could assume, right? This will, you want the values to be below 1 in your wall Y plus. If it's over 1, you're going to have to check your mesh and refine it a bit more. More than likely, if your wall Y plus is too high, then you need to increase your boundary layer thickness. If it's still too high, then probably increase the number of layers, and yeah. But your wall Y plus is basically mainly a focus on your boundary layer, on your meshing over your boundary layer. If it's under 1, then it's okay. In here, we get around like 0.94. That's alright. It's good. You know, as long as it's under 1, I'm fine with it. So, that's good. Now, here you go. Now for this project, we're going to need our velocity contours. So we're just going to put our velocity contours here. Pretty simple. Yeah, looks good. You know, like a needle going through. It's to be expected. Good. And then pressure contour. Looks good. Alright. We will also probably need, this is static. We will also need a total and all that, so I'm going to just label it static. New. And yeah, this is going to be a little boring, but we're just going to have to do this. Okay. That looks good. Nice. I mean, I don't really need the absolute pressure. Just probably delete that. Don't need it. Yeah, we need dynamic, total, static, and then our velocities. That's all we need. So yeah, let's go down. And then we're going to be doing next our plots. First one I'm going to be doing is wall shear stress. Our wall shear stress here will be, where is it? Wall fluxes, and then, yeah, wall shear stress. There you go. And on the plate, there you go. Now this is all we need. We will need to get a skin friction coefficient. But for that, we will export this plot and then use the function. Let me pull it up here. Let me see if I can find it. Right here. Wait 1 minute. Okay. So this is the function that we have. This is from a group of people in the class. The function here will be this one in the bottom. If you can see my mouse, the CF will equal your wall shear stress divided by 1/2 times your density times your velocity squared. Essentially, your wall shear stress divided by 0.5 times your density, which is 1.225, and then times the velocity, our reference velocity, which will be 15 meters a second squared. We got to export that into Excel and then graph it. That's pretty fine. And for the drag, it's basically something similar, except using the drag coefficient function, which I'll put up again. It's this one right here. This one's for the flat plate. This is your drag force, which is what we have, divided by 1/2 times your density times velocity squared times the length of the plate. So yeah, that's basically it. That's gonna be done in Excel. I'm not gonna be showing it here in the video, but yeah. Thank you for watching.